The LinBot, from California State University, Northridge. The LinBot is an autonomous vehicle designed from the ground up to accomplish a specific series of challenges. Those challenges are set by the Intelligent Ground Vehicle Competition Committee and are tested here. Their 15th annual competition, this year in Rochester, Michigan. Here, teams from around the country gather their creations to test against their peers. One of the most daunting tasks is the autonomous challenge. The challenge requires the robot to navigate a preset obstacle course. The robot must guide itself using the painted white lines on the grass and avoid hitting the fluorescent barrels that riddle the course. But why such a simple challenge? And why are these challenges such a costly endeavor?
Building an autonomous robot is neither a cheap or simple objective, but it's an important one. It represents one of the pinnacles of the robotics. A robot that can think and act on its own. For students, it's a way to introduce them to the digital world, to show that a robot cannot work by itself without enormous help. In addition, it brings together students from varied backgrounds and engineering fields in order to work on the several systems necessary to have a working vehicle.
The vehicle is divided up into 4 systems. One of the most important systems for the previously shown challenge is the visioning system.
Robots can't see the way we do. The input from a camera is just a map of pixels to the computer. In order for the data to be useful, the robot must eventually convert the data into a direction that the vehicle needs to travel. To do this, the software applies a series of filters to the camera data until the final image consists mostly of pixels from the 2 white lines. Then, a best fit line formula, such as the Hall transform, is applied to the pixels in order to obtain a formula for the lines. Finally, the 2 formulas are used to determine the direction the robot has to travel.
For the navigation challenge, vision takes a backseat to the more global systems present in the vehicle. Here, the robot is given a set of coordinates it must travel to, while avoiding obstacles, and find its way back to the starting point.
The challenge requires 3 sensors to complete. The laser rangefinder, or the LRF, scans an area of 180 degrees in front of the vehicle and determines if there's an obstacle in the way. The digital compass determines which way the vehicle is heading to an accuracy of 1 degree, and the GPS can determine the vehicle's location to an accuracy of 4 inches, necessary for determining how much further the waypoint is and when the vehicle has reached it.
The vehicle is controlled by 2 computer systems. The PXI is a Pentium 4 class computer that controls most of the sensors and motors in the system. For vision calculations, a consumer laptop with a FireWire port is used. Both of these systems are run simultaneously using shared variables in a program called LabVIEW.
LabVIEW. This graphical programming software is the center of the entire project. The code, or algorithm, that controls the robot has been developed over several years of teams and students from mechanical, electrical, and computer science majors. Every program consists of several subprograms, and all must be computed in a matter of milliseconds while the vehicle is running. The robot's motion, also controlled by LabVIEW, promotes response to commands over power.
The robot moves via 2 servo motors, each with a 20-to-1 gear reduction and a maximum 3/4 horsepower. The robot is capable of responding within a tenth of a second, which means the speed must be controlled accordingly. The robot is programmed to travel no faster than 5 miles per hour, which with our current response time translates to 9 inches of travel before the code is implemented.
But, like any system, the LinBot still has areas for improvement.
A more powerful and compact computer system will allow for size advantages and faster program execution.
Better cameras allow for greater control over the input and more accurate results.
Optimizing the algorithm would decrease computer load, increase the accuracy of the heading information, and allow for faster speeds.
With the help of generous companies and alumni, the autonomous vehicle project rolls on, and it and its students prepare for its next competition in the summer of 2008. For more information on the Intelligent Ground Vehicle Project, please visit our website at www.ecs.csun.edu/IGV, email us at igvt@csun.edu, or call us at 818-677-2760.